Hello and welcome to part 4 of the video series on the LinuxKI toolset. As mentioned in previous sessions, LinuxKI is a trace-based performance analysis tool. So in today's session, we'll be examining the KI trace data itself. In part 3 of the video series, we learned how to collect a LinuxKI trace dump using the runKI script and how to create a set of trace-based reports using the KI all script. Today, we'll focus on the ASCII trace data. Normally, we don't begin our analysis with the actual trace data, but it's important to understand LinuxKI from the ground up as you build your knowledge about the tool. In order to limit the overhead of the tracing, but still provide a rich set of information, a small set of trace points were chosen, which provides the best insight into performance and helps answer the questions: when it's running, what's it doing? And when it's waiting, what's it waiting on? We will get trace events for every system call, entry, and exit, scheduler events for context switches and wake-ups, block I/O events, interrupt or IRQ events, and a few other events such as the CPU profiling event known as hard clocks. After executing the KI all script to process the KI trace dump, you can find the KI ASCII trace data in the file named KI followed by the timestamp. This large flat text file contains a lot of trace data, so you would not view or analyze the trace data unless you're looking for something specific or to understand the order in which trace events occur. The example trace data seen here represents a single system call for the task with the process ID of 31549. In each trace record, you can find the relative timestamps in seconds since the trace was started, the CPU number, the process ID, the task group ID, and the trace event type, as well as the variable information for each trace event. You can see the system call events, the scheduler events, the block I/O events, and we even captured one hard clock trace event. However, the power of LinuxKI is not in the ASCII trace data, but in what it does with the trace data. LinuxKI compiles a large number of statistics on the trace events and presents the statistics in a number of ways. These statistics are simply calculated by the time between the events. For example, the time between the system call entry and the sched switch is the amount of time the task spent executing system CPU cycles. The time between the sched switch and the subsequent sched wake up of the same process is the amount of time the task spent sleeping. LinuxKI keeps track of the system call the task was sleeping in, as well as the kernel function and stack trace where the task went to sleep. Note that LinuxKI will attempt to trace the kernel portion of the stack and the user portion of the stack as well. This helps answer the question: when it's waiting, what is it waiting on? Not only that, but LinuxKI also keeps track of which tasks perform the wake-ups, so we can tell how the various tasks either cooperate or compete for resources. For this particular stack trace, we can see the process was doing an ext4 file write when it encountered a wait on a mutex log. The time between the sched wake up and the sched switch to put the task back on the CPU is the run queue time, or the time spent transitioning to the CPU or waiting for CPU. LinuxKI continues to calculate the statistics during the life of the task for the duration of the trace, which is then used to produce reports that paint a very vivid picture of each task and much, much more. We also get detailed information regarding the I/O, the time between when an I/O is inserted into the block device and subsequently issued to the lower layers is the time the I/O spent on the block device queue, or the queue time. The time between the block request issue and the block request completion is the amount of time the I/O spent at the lower layers in the hardware, also known as the service time. This information is collected at the SCSI device layer, and it is also collected at the multipath device layer. These trace events provide information on the various I/O characteristics such as reads and writes, I/O sizes, random I/O versus sequential I/O, and much more. LinuxKI will provide a view into the I/O unlike any other tools available on Linux. Again, the actual trace data is vitally important, but what LinuxKI does with the trace data is what makes it such a valuable performance analysis tool. We'll start looking at that data in part 5 of the video series next. If you need additional information on LinuxKI, be sure to check out the LinuxKI wiki page where you'll find links to all the video sessions and more. I hope you have enjoyed today's session and see you next time.